Good afternoon, everybody. Thank you for your attending this webinar today. I would like, before we start the webinar, I would like to present some information regarding Professor Abdullah. Can I share? Let me share the page. Okay. Okay. Abdullah.
Yeah, you pronounced very well, no problem.
Okay, thank you. He pursued his doctorate graduate at Tokyo University of Agriculture and Technology, Faculty of Engineering, Department of Electronics and Information Engineering, Japan, and he finished his postgraduate study in 2009 at Tokyo University of Agriculture and Technology, Faculty of Engineering, Department of Electrical and Electronics Engineering, Japan, and did his undergraduate degree in 2005 from Karadeniz Technical University, Mühendislik Fakültesi Electronic, Turkey. And he speaks fluently in English and also in Japan. His research area is in electrical and electronic engineering, renewable energy, optical materials and devices, semiconducting materials and devices, engineering and technology. And this is his contact. You may contact Professor Abdullah through email or his web page. Okay, Professor Abdullah, maybe I don't want to waste more time, so I'll give you time to present your result of your research, maybe in 1.5 hours. Thank you very much. Please, Professor Abdullah,
Okay,
over to
thank you
you.
very much. Thank you very much for your introduction. Let me share the slides first. Okay, and I will take a pointer here. You can see the slide, right?
Yes, it's already there.
Okay, hello everyone. Thank you very much again for your introduction. My name is Abdullah Üzüm, and today I will be talking about renewable energy, photovoltaics, and advanced solar cell designs. Step by step, after the overview of renewable energy and energy station in the market, we will talk mostly about the advanced solar cell designs. Let me introduce myself first, but it's already introduced. That's why I will not spend some time here. I'm now working on Karadeniz Technical University. So I will give some information before I start about our university, which is Karadeniz Technical University. We have 12 faculties with 80 programs, and Karadeniz Technical University offer 6 graduate schools with 88 masters and 53 doctoral program, and 1 language school, and 8 vocational schools. We have around 31,000 students, enrolled students, and among them 2,108 are international students. They are coming from different countries, 104 countries. And we have alumnians of 261,000 actually. So here is some landscapes from our city, Trabzon, and I will show the campus. This is our campus, Karadeniz Technical University. Here is the medicine faculty and the hospital, and dormitories, and some other parts of the universities around. So let me start with the outline. Here's the outline of my talk today. I will start with the general overview of energy situation in the world and the share of renewable energy and why we try to use renewable energy. And then we will see it again. I will remind you some fundamentals, some basics of the solar cells. And mostly we will be talking about crystalline silicon solar cells with the structure of BSF, PERC, TOPCon structures especially. And then I will talk about the perovskite and tandem solar cells and designs, different designs. And then we will look at the current situation of these kind of technologies in the market. And then what is the forecast we have. Then I will summarize the talk for today. Let's start with the global energy demand. That here is the global energy demand graph. Shows roughly one third of the world's energy supply comes from the renewable energies, but still 2/3 of it lies on the fossil fuels. And that's important because fossil fuels are the main cause for the carbon dioxide emission that we try to reduce. And if you look at the carbon dioxide emission trend, we can see that the trend of the rise is continuing steadily upwards. And the main reason for that is the energy consumption, especially fossil fuels. That's why we are searching to use and more installments of renewable energy or low carbon dioxide emission energies. That also affects the temperature, the rise of the temperature. That's why it's important. This graph shows the global energy mix scenario. If you check the reports, you will see a lot of different scenarios. And here is this one is from International Energy Agency with the scenarios of stated policies, announced pledges scenario, and net zero emission scenario. Especially this net zero emission scenario is the main target to have a zero emission. But when we look at this, we can understand under every scenario almost that fossil fuels will have the peak in coming few years and then gradually falls, and the clean energy usage will be significantly increased up to 2050 and will be continuous. And when we look at the installed capacity, clean power capacity, when I say clean power, we can understand the hydro, nuclear, bioenergy, wind, solar PV, and other low emission technologies. We can see that solar PV and the wind actually are the lead on the growth, especially this lead of a significant increase of solar PV is very important for the net zero emissions. And actually, it is expected that if we think about the electricity generation, it's expected that the share of wind and solar PV will be around 40% of the energy demand in the electricity generation up by 2035. Of course, to have this kind of transition from fossil fuels to renewable energy, a significant aggressive investment to the renewable energy, clean energy sources is needed. And here you can see some scenarios and the comparison of advanced economies, China and other developing economies, that what is the pledged scenario for the net emission, net zero emission, what we need. And you can see directly that actually an aggressive investment on the clean energy sector will be needed, especially for developing countries here. The difference is very large. When we look at the prices here, we see that the prices falling down gradually for solar systems, wind, battery storage systems. Actually, this is a very good fact that the falling costs makes these kind of technologies more achievable and more attractive. That's why we can say it's important. So here I will ask the question that why is solar PV important? First thing, you can imagine maybe the electricity generation without carbon dioxide emission during operation and using the abundant sunlight makes solar PV clean and sustainable. The second reason may be the modularity and flexibility of it, that you can apply solar PV in a small scale, like rooftops, street lights, etc., and utility scale for solar farms, for example, in megawatt scale, etc. And energy security and independence also can be other matter that solar PV can help to reduce the dependence on the fossil fuels. And the technological innovations, technological improvements in silicon perovskite and tandem PV technologies improves with high efficiency and low cost. That's why it makes to use solar PV more attractively. So the integration with the other energy systems is other advantage of solar PV, that PV can be combined with energy storage and smart grids that can provide flexible power. In this slide, actually it's a nice slide to show that what kind of manufacturing capacity we have in solar PV. These columns shows the manufacturing capacity of polysilicon wafers, cells, and modules. And these blue dot here, you can see is the installations. And when we look at the 2014, we can see that the installations are less than 50% of the capacity actually, but up to 2030, we may have installations closer to the manufacturing capacity, which is important to achieve renewable energy sources in the market. So at this point, I will remind you some fundamentals, some basics of the solar cell and its operation, and then we will continue with the designs. First, we know that you should remember that solar cell actually is a p-n junction, and that's why to understand how solar PV works, solar cell works, we need to understand p-n junction, working of p-n junction first. And we will see that to maximize the efficiency of a solar cell, actually we need to maximize the carrier generation and to minimizing the recombination. And you will see that every improvement now making solar PV more efficient is about, especially for crystalline silicon solar cells, is about maximizing the carrier generation and minimizing the recombination processes. This is a typical p-n junction schematic in equilibrium. Remember that we have n-type material with majority carriers of electrons. These dots are electrons with minority carriers of holes on n side. And on p side, we have majority carriers of holes and minority carriers of electrons. And when a p-n junction formed, we know that the first thing comes is the diffusion of electrons from n side to p side. And if there is no biasing, then after some time, a built-in electrical field will be formed in on the junction, and after the equilibrium reached, we can say it will halt, it will stop the carrier transfer from N side to P side. Because of this electrical field, it will repel electrons and holes to move other side. And we call this region as the depletion region, chargeless region, remember. So what this electrical field does, actually a barrier, right? This is the energy scale. A barrier is here formed because of the electrical field, so the electrons cannot easily move from N side to P side. And if you apply a forward bias, for example, you can decrease this barrier and make electrons more easily move. And if you apply a reverse bias, you can increase this barrier, and it will be very hard for carriers to jump off this barrier, right? And that's actually how diode works, that it conducts current from one side to other side. If you have positive voltage of 0.6, for example, for silicon, and if in negative voltage drops on it, it will not get conducted, right? So the other thing I want you to remember is the optical absorption and light generated current. We know that, remember that semiconductor materials actually have moderate band gaps that you can manipulate. And E sub C here is the minimum point of the first empty band, which is the conduction band we call. And EV here is the maximum point of the valence band filled with electrons. The last band filled with electrons is the valence band. So if you have an energy, if the photon energy comes with the less than energy band gap here of the semiconductor, you know that it will not be enough to break this electron from the valence band and to make it jump to the conduction band. And the other scenario is if you have excessive energy larger than the energy band gap, you can break that electron from valence band and it can jump to the conduction band. And then after some time, it will relax to the conduction band edge, right? But both of these are losses. And when I talk about tandem solar cells, I want you to remember this kind of phenomenon because it is related. I will remind you again. So what happens under the illumination? We know that this is the p-n junction diode, let's say, and when the illumination comes on as a solar cell, a p-n junction, as I said in the previous slide, the photons with the energy greater than the energy gap will produce electron hole pairs. And with this electrical field on the junction, these electron and hole will be separated. And when you close the circuit, it will conduct through the load, right? So how we can show this illumination effect on the circuit diagram, you can see that actually it's a current source, right? Because we have extra movement, extra carriers of electrons in the circuit. That's why we add a current source in the circuit, and now the circuit looks like this. And if you apply Kirchhoff's law on this circuit and solve it for ID, you may have this kind of equation. And here, to reach the solar cell parameters, we have two boundaries. The first boundary is the open circuit condition. When the circuit is open circuited, that is zero. And if you substitute ID with the zero and solve you can derive the equation for V sub OC, VOC, open circuit voltage. And the other boundary condition is the short circuit current. And in the short circuit current condition, you know that the VD is zero. And if you substitute VD with zero, you will have ISC equal to minus IL, which is the illuminated current, this effect. Okay. So we can say with the illumination, first thing is the carrier generation, electron hole pair generation. And the second one is the charge separation of these electron hole pairs with the electrical field. And the third step is the charge collection, carrier collection through the contacts if you complete it with the load. Okay. So, but in practice, we add series resistance here and shunt resistance in the circuit because in practice we have a lot of losses. For example, this series resistance stands for the composed of the losses like bulk resistivity of the material, the contact resistivity, and the resistivity between contacts and the bulk interconnections like resistivities. And for the shunt, resistance composed of the junction actually. If there's a leakage on the junction or the edges, the precipitates inside it, or the impurities, crystal defects like this. So for the maximum net current, we want RS, series resistance, very low, and the shunt resistance very large to have the maximum current out of the circuit. And if you derive the equation, the previous equation with shunt resistance and the series resistance, and if you apply the Kirchhoff's law for this node, for example, you can solve it like this. Okay, and that brings us to the IV curve. Now we know that the GSC is the current that you can read when the voltage is 0, and VOC is the voltage value you can read when the current is 0, right? And this dashed line here is the dark IV curve of a PN junction. In the dark, if you measure the solar cell in the dark, you will have kind of IV curve like this as a diode, right? Because of the PN junction. But when you have illumination on it, you will see that this current jumps to this level, to the IL level. This level is actually the illuminated current level, and then it follows the diode curve. Okay, so that means actually that this curve means that your solar cell is working on some point of this curve. Okay, that means your solar cell is working on some point of this curve, and you can say that at some point here you must have peak power, maximum power, right? Let's say that this point is the maximum power point, and at the maximum power point we have V sub M as the maximum voltage you can have, and J sub M, the maximum current density, or current, let's say, and the peak power will be IM times VM, right? That's why we have maximum power points trackers. So the other parameter of solar cell is the fill factor. Fill factor is the IM times VM divided by ISC times VOC, which is actually, if you closely look at the IV curve, you see that VM times IM is the area of this rectangle, and ISC times VOC is the maximum possible rectangle here. So actually it shows how much your maximum power point can fill the maximum rectangle. You can imagine it like this. That we call fill factor. And the conversion efficiency we have from a solar cell will be output power divided by the input power. Now we have the output power of the maximum at the maximum point, IM times VM, divided by the input power. And IM times, you can substitute IM times VM as FF, fill factor times ISC times VOC, divided by the input power. That can be different. I mean, it will depend to radiation. If it is under the sun, it depends on the radiation from sun, how much it comes. But standard test condition is one sun condition we call for 1000 watt per meter square. So this is the main formula that we calculate efficiency. Okay. So after I remind you some basics like this, let's see what type of solar cells we have, and then we will start to talk about them. First thing is the first generation solar cells we call is the crystalline silicon solar cells, consisting of monocrystalline and multicrystalline. And second generation solar cells are the thin film solar cells, CIGS, cadmium telluride, amorphous, CZTS, thin film solar cells. And third generation is called 3-5 compounds, is 2-6 compound solar cells, and emerging technologies like perovskite, dye-synthesized organic tandem solar cells, etc. And today, we will be talking on the designs of crystalline silicon, monocrystalline silicon solar cells, especially because still around 98% of the cells in the market we see outside is monocrystalline silicon solar cells. That's why I will explain them first with the structures, and then we will talk about the perovskite solar cells, the emerging technologies, and the tandem solar cells. Okay. So this is the energy best research cell efficiency graph provided by NREL. It is very famous. You might see it before, but this graph shows the trend. It tracks the solar cell efficiencies over time, confirmed solar cell efficiencies over time, divided by some groups. We have multi-junction solar cells here, crystalline silicon solar cells that we will be talking, and thin film technologies, the green one, emerging solar cells, and recently hybrid tandems has been also added to the chart that we will talking today. Let's look first the crystalline silicon solar cell. Over decade, you can see that the crystalline silicon solar cell efficiencies increased over the decade, but it is almost stabilized, and the increase become more stable because it is very close to the theoretical limit. That's why researchers try to find other technologies. And now the advances in crystalline silicon technologies are about the incremental effects. That means the passivation quality, the texturing quality, light trapping effect, etc. So if you look closer, here, we have the maximum efficiency of silicon solar cell, around 26% efficiency for single crystal, non-concentrated solar cell that we were talking. But the maximum efficiency is for HIT, which is silicon heterojunction structure. And for the emerging PV, we see that the research and the progress of emerging PV is very fast after 2010. Actually, it started with EPFL around 1990s with the dye-synthesized solar cells and then the organic solar cells. But recently, especially, perovskite solar cells shows very rapid progress and in the cell efficiencies. If we look closer, we can see that perovskite solar cells actually achieved around 30% efficiencies and tandems exceeding it. This tandem is all perovskite tandem solar cells. That's why it is a different group. And recently, as I said, the hybrid tandems added to the chart. That today we will talk about perovskite silicon solar cell tandems, for example. And there are other confirmed efficiencies of perovskite organic solar cells tandems, perovskite CIGS, and 3,5 compounds with silicon tandem solar cells. And they are exceeding, reaching 34.6 efficiency by Longi, reported by Longi. So let's talk about the crystalline silicon solar cells here, with full BSF, PERC, and TOPCon especially. First, I will show the typical structure, very conventional structure of the silicon solar cell, P-type silicon solar cell. This is the typical structure with the P-type silicon base and M+ emitter layer on it. Of course, the applied texturing and anti-reflection coating on it, and then P+ back surface field on the back side, aluminum contacts and silver contacts on front side. So if we divide this to the 4 main steps, we will say that the manufacturing of the conventional typical silicon solar cells start with the texturing process to reduce the reflection losses. We will be talking about that in coming slide. And then the emitter formation to make the PN junction. When you form here an emitter, you have here PN junction, right? And then the anti-reflection coating on it to further reduce the recombination reflection losses on the surface. And then aluminum back contact formation and front contact formations. These are screen printing contacts, dried, and afterwards they are fired. After the firing, you have the contact on front side, and with aluminum silicium alloy, you have P+ BSF layer on backside. If we talk about them one by one very briefly, we have texturing on the front surface, because if the light comes, if the photons comes on the flat surface, for example, like almost 40% of it reflects off the surface. And what we try to do with the texturing process is causing multiple reflections and try to keep as much light as possible, as much photons as possible into the solar cell. And by this, we have less reflection on the surface. Here are some real images on the surface of solar silicon surface, This left one, these are microscope images, optical microscope, I guess, and these are SEM images and the cross-section images. Actually, both are similar, but the etching process is different. This one is sodium hydroxide etched process, I guess, and this one is the potassium hydroxide etch. You see that the formations are similar. You have random pyramids on the surface and very clear, nice pyramids on the surface that will decrease the reflection on the front surface. After that, again, we have N-type emitter formation. Standard technique for this is the focal diffusion, but it can be done completed with sol gel processes, spray or skin printing processes. The focal diffusion actually, focal is actually a liquid, and it happens into 2 steps. In the first step, focal liquid is bubbled with N2 gas, and this evaporated focal gas goes into the tube or tank like this, and on the surface of the silicon wafers. These are silicon wafers here. And then this is the low temperature process. We call it pre-deposition. And after the deposition is completed, we halt the N2 gas and introduce oxygen to the tank, and the reaction that will produce potassium phosphor pentoxide, and it reacts with silicon and diffuse into the silicon wafer and forms N layer. The other processes like spray deposition or spin printing deposition are similar, but in that case, you just spin or spray or print the phosphor source on the surface of the wafer, and then you directly, with the appropriate thermal profile, you can directly make the thermal process and have the N-type formation on the front surface. So that's the N plus emitter formation. And next one is the anti-reflection coating. As you can imagine, we have losses, optical losses, electrical losses, as I said. To reduce the optical losses on the surface, the reflection losses, we can say, because we have contacts on the front surface, and incoming light can reflect from these contacts, and these are the losses that you can not do anything because it will reflect from the contact surface. But what we try to do is to reduce the illuminated surface reflections, like this one. And also there are some losses that caused by the reflection on the back surface. And you will see that in PERC design, in TOPCon design that we will be talking about, are actually helping to reduce these kind of reflections too. The anti-reflection coating phenomena actually depends on the destructive interference. Destructive interference is happening like this. If imagine two waves, they are in the phase, they are coherent. If they interface, they will double in the constructing interface if they are in phase. But if they are out of phase, 180 degrees, then they will neutralize each other and there will be no reflection. That's the case we try to do with the anti-reflection coatings. For example, here, N0 is the refractive index of the air or the ambient you have. N2 is the silicon here, and N1 is the anti-reflection coating for the case of single layer anti-reflection coating. And if you have this kind of destructive reflectance, then the reflected light here will be zero. But that happens only one, the zero reflection happens only one wavelength, which is with the thickness of 1/4 of the specific wavelength you have. But we can make better reflections. This is the single layer anti-reflection coating. With the one layer anti-reflection coating, you have transmitted light, you have reflected light, you have transmitted light and reflected light for each case. And with the double anti-reflection coating, you have double layer anti-reflection coating. These have gradually increased refractive indexes. For example, 0 is the air is 1, the silicon refractive index of silicon is 4.3, around 4, and N1 and N2 is gradually increased refractive indexes. Or you can do multi-layer anti-reflection coatings, and in this case, again, you can calculate it with different techniques that with the transmitted and reflected lights, transmitted and reflected lights for each case. Here I show you some examples from our previous works. For example, hafnium oxide as an anti-reflection layer on the surface of silicon. This is the measured value around 11%, and these are the calculated and simulated values, which are very similar, that you have almost zero reflection on the around the peak of the solar spectrum. Solar spectrum comes like this. That's why we want the zero reflection at the peak of the solar spectrum. That's why you will see that all reported data are around 550s. For the double anti-reflection coating, here you see the comparisons very well. That this dashed line measurement is the flat silicon surface without anti-reflection coating, and you see that the reflectance is above average reflectance is around 40%, right? And if you texture that and without anti-reflection coating, only texturing, you can decrease this reflection to this green dashed line, okay? And if you apply, or in this case, we apply double anti-reflection coating. If we apply anti-reflection coating on the flat surface, you can decrease it like this. And if you apply it on the textured surface, you can further decrease the reflection like this red one, okay? And this is the case for aluminum oxide, titanium oxide anti-reflection coating. And the other one is multiple layer anti-reflection coatings. These are the calculation and simulations. With multiple layers, you can reduce the reflectance on the surface in a very wide range of the spectrum, like this. And last manufacturing process for the silicon solar cell is the metallization. Metallization process for aluminum and silver is very similar. That's why I will explain it with the aluminum on backside. But you can imagine that same things going on the silver for the front side. Okay, and usually the cold-fired, the process temperature process is at the same time. So what we do is you screen print the aluminum on the surface of the silicon wafer at room temperature, and with the appropriate profile here, here's an example, with the appropriate profile like this, the alloying starts around 660s, and these aluminum and silicon alloy starts, and with the increasing of the temperature further, and when it comes to peak, you have fully liquid aluminum inside the silicon, and when it degrees like this very fast, and you can change this profile, but the shape is very similar. You will see that the solidification takes place, and you have a BSF, P plus BSF here, and the residue of the aluminum on the back side as the contact. So again, these are the aluminum case, which is very similar with the front case. And in practice, what we do is we screen print aluminum on backside, dry it, and then flip over the wafer, screen print the silver on the front side, and then dry it. And after that, both of them will go to the same profile like this for the firing, we call firing. So by far, I explained how full BSF crystalline silicon solar cells looks like, how of structure it has, and how we fabricate it very simply. And if you look at these fabrication sequences, you see that this is the case of cell, which is isolated emitter rear contact solar cell. If we look at this schematic here, you see that the backside of this solar cell is different from field solar cell. In the back surface field solar cell, we had P plus layer all over the back surface and aluminum all over the back surface. What we try to do with PERC structure is local contacts to decrease the recombination, and passivated rear layer here to make the passivation to decrease the recombinations, and that will also increase the light trapping on the light trapping. It will reflect back and increase the absorbance. Okay, you can. This is the bifacial case. You can do this monofacial. Monofacial means the back side is opaque and the light comes from the front side only, and the efficiency you get from the solar cell is depending on the front side illumination only. But in bifacial solar cells, the reflected light on the back also comes inside the solar cell and it will contribute to the efficiency. And this is the bifacial case of PERC solar cell. So the top-gun solar cell is actually the top-gun architecture, the top-gun structure design also actually uses the idea of PERC, a similar idea. In this case, we have silicon dioxide, very thin, thick silicon dioxide layer, which is 1 or 2 nanometers, and highly doped polysilicon on backside to make the barrier I will show in next slide, and the anti-reflection and passivation on the backside. And we have AG and contacts and the front surface contacts. The other type is widely studied is the back contact solar cells. If you see that the sequences are similar, but the back contact solar cell is the main advantage of the back contact solar cell is you have no contact on the front side. That's why the whole area of the front side will receive the light. That means you can convert the light, you can have more light on the front surface, and both contacts are on the back side. Of course, it has some challenges itself. And the other thing you may realize is PERC solar cell here is the P-type, usually top-gun N-type, and the back contact is also N-type here. But you can make this N-type, P-type solar cells with monofacial, bifacial. But these are the mainstream now. That's why I only show these structures. Here is the energy band diagram for the PERC solar cell. This energy band diagram also counts for the full BSF structure, but it is the same. It shows the role of the P plus BSF, back surface field. We call it back surface field because it is the field on the back surface, and it helps to avoid recombination on the backside of electrons. So electrons will be repelled like this, and holes can go through. That's why recombination will be decreased. And in top-gun structure, we have very thin silicon dioxide tunneling layer. It is very thin, and it also has passivation effect. And with this, thanks to the thickness of it, it can allow quantum tunneling, and then electrons can tunnel through the layer. And with the help of the heavily doped N side on the back, you have the barrier like this, and holes are repelling. So you can also avoid the recombination here. So after you manufacture PERC or TOPCon or full BSF structure solar cells, it is seriously connected like this. These are seriously connected silicon wafers, and they are encapsulated on the front surface, encapsulated on the back surface. They are encapsulated to isolate them from the ambient. And then backsheet, front glass, and the aluminum frame to make it rigid, and the junction box on the backside. And here are the weight percentage of the components that you can, the composition of the solar panel, you can see, and more than 70% is weight is depending on the glass. So now let's talk about the perovskite and tandem solar cells. These are the emerging technology, and still we don't have them in the market. But when we talk about the current station and forecast, we will look the possibilities. So at first, we can say that perovskite actually is the name of the crystal structure with three elements, ABX3 structure, and the A is the cations, and B is the metals, and X are the halides, iodine, bromine, or chlorine. You can add here. And this is the typical mesoscopic structure of perovskite solar cell, which has titanium oxide, electron transfer layer, the absorber layer as the methylammonium lead iodide, methylammonium lead iodide. This part is methylammonium, and lead and iodide. So it is a BX3 structure, and the spiral method on the as the whole transfer layer, and then the contact. This is the structure of a perovskite solar cells, and this is the mesoscopic structure. You can make it planar structure, inverted planar structure, with changing the design upwards. And here is the energy diagram that shows how the principle is the same. The working principle is the same, but this shows how electron and hole pairs after generation, how they move towards the respective contacts. The first and very important advantage of the perovskite solar cells is the band gap tunability. You can tune the band gap of perovskite material. Here are the colloidal nanoparticles of a crystal or a perovskite under the UV illumination. You see that they have different colors, and with the PL, they show different peaks. That means different band gaps. And with changing the halides, changing the metals or cations, you can change the band gap. And mixing the halides, mixing the cations, mixing the metals, you can have intermediate band gaps between them even. So this is, for example, from 1.77 to 3.06 electron volts, you can have different band gaps. And here is a systematic change of the band gap of methylammonium lead iodide by adding the bromide content in it. And here is how they add the bromide content. And you see that with the bromide content increased, the absorption decreased because of the increasing of band gap and to the lower wavelengths. And if you check the color, and if you produce it really, you see that the color changes from black brown to the orange with the full bromide, and the band gap changes from 1.65, 56, 55 around to the 2.23. This is the methylammonium lead iodide and methylammonium lead bromide mostly here. Okay, so if we look at the crystal structure of it, or the surface, perovskite surface, you can see the uniform structure of the methylammonium lead iodide surface, and with increasing the bromide content in it, actually the crystal structure changes, as you can confirm in these images. So here in this chart, it is shown with different metals, different cations, different metals, and different halides with different compositions. you have different band gaps with the different LUMO and HOMO levels. You can think it as conduction and valence band. This is very useful for tandem structures. When we design tandems, it is very useful. You will see that you can change band gap like this, and even you can further change these band gaps with mixing them. These are not mixed. With mixing halides, mixing metals and others, you can have different band gaps, and it provides you flexibility in design of the solar cells. So these are the perovskite basics, and the first efforts of the perovskite, the use of perovskite in the solar cell structure is back 2009. 2009 with using the perovskite as a sensitizer in dye-sensitized solar cells. But at that time, it was very new material and it degrades very fast in the electrolyte. That's why still 3.8% efficiency is reported. And after that, after 3 years, the perovskite structure that is very similar to the one I showed with spiro method as the whole transfer material, as the first, maybe one of the first solid state solar cell structure with perovskite is formed with the efficiency of 9.7. At that time, it was a single deposition process, and after that, double deposition process was introduced, and the efficiency of perovskite rised gradually. And remember the first graph, the efficiency graph, that the efficiency of perovskite progress is very fast, very rapid. And this is a good thing for the research, but still not state of art. And by coming years, this is a study from 2022, approaches being going on with the different materials, different interfaces, different hole, different electron transfer materials. This is an example for the different tin oxide with some additives for the electron transfer layer, and they show the efficiency of 21.2%. And with this, I want to move to the tandem structures. We'll show 3 of these structures here. Tandem structures, first thing you need to know is 2 different, and the main goal here is having a high band gap material to absorb the lower wavelength, and having a low band gap material larger wavelength of the spectrum. Okay, and that's why we have a top cell with high band gap material. It filters the light, emits the light in this part, for example, and it filters the rest of the light. The low band gap material will receive the light and produce efficiency separately. And with that, maybe when you think about it, the first thing comes to mind as a design to split them, to use spectrum splitting like this, having 4 terminal, one solar cell here with low band gap, the other one is here with the high. You split one portion of the light here, the other portion of the light here, and you have easily, with 4 contacts, very high efficiency. But in practice, it's not easy to apply. That's why it's not that much feasible. Then the other structures, the other possible structure is the 4 terminal, having the top cell with high band gap solar cell, and have 2 contacts for them, and the lower cell with the low band gap again, 2 contacts for it, and you have 4 terminals. Okay, but in this case, you have independent contacts. That's why you need more wirings, etc. And you have shading laws, etc. But the advantage of it, you don't need current match. Current matching is very important for high efficiency that you can see for the 2-terminal structure. And you can also have 3-terminal structure, but I show here for a 2-terminal. For the 2-terminal structure, you have 2 contacts. One is from high band gap solar cell, and the other one from the low band gap solar cell. So you have 2 contacts, and that means actually you have these 2 cells serially connected, right? Because you have 2 contacts. That means you can add the voltage of 2 solar cell, but there will be single current flows. That's why if one of these solar cells have the lowest current, that will be the current you have in the circuit. That's why we say that the current matching is important for 2-terminal tandem solar cells. Here I can show you the case that if you use perovskite material as a top cell, high band gap top cell material, and if you have silicon as the bottom cell, low band gap bottom cell, you can imagine that the top cell material have received the shorter wavelength light, and the bottom cell will receive the higher wavelengths of light, and you can cover this range of spectrum. Remember the light absorption that here I depicted again, that with the incoming photons of energy, you can have that much energy and you can create electron hole pairs here or here. But if the energy is low, you cannot, the electrons cannot jump to the upper energy band. So that will be lost. Here, for example, in this example, this part is lost, right? So here the question can be, why to use perovskite solar cells as a top cell? The first thing, again, is the tunable band gap. You can easily tune the band gap of a solar cell, and the high absorption coefficient of perovskite, if you compare with silicon, is very high. It is important. You can imagine it like this. For the same amount of light, for example, if you want to absorb 100% of it, you may need very thick silicon wafer. But with the high absorption coefficient, like perovskite, you can absorb the same light, same amount of light in very thin layer, like micrometer thick. Okay, that's why it is important. And solution process like low-cost processes make it very attractive to use. But still, there are some challenges like toxicity of the lead we use in it and stability. But you can find a lot of researchers you have perovskite not including the lead, for example, but they cannot reach the same efficiency now. So in this part, I will show you some earlier tandem studies and recent tandem studies. One of the earlier tandem studies has been carried out when I was in postdoc, for example. I will give some examples from that time too. That, for example, this is the thing we did at that time. This is back in 2015. We used the perovskite top cell as the high band gap solar cell and crystalline silicon bottom cell as the low band gap bottom cell. And you have this kind of structure, right? But again, the most important thing here is the recombination junction. The junction the junction that they have this interface is very important. We will talk about it from now on. First, at that time, again, we used the simple mesoscopic structure of the perovskite solar cell with titanium dioxide or electron transfer layer with the metal aluminum lead iodide absorber layer and spirometallics as the hole transfer layer, and back contact as thin gold. And for the bottom cell, we prepared at that time a simple full BASF solar cell without front contact. And the first thing, this is one of the first studies of tandem solar cells. That's why I guess it is important. First thing, what we did is we made a very thin layer on the perovskite layer. This is 2 nanometers, 1.5 or something. And then we sputtered ITO on that, optimize it seriously. You will see in coming slides that actually this is not applicable for monolithic tandem structures. But because in the monolithic tandem structures, you need to grow, you need to fabricate your cell above these layers, right? The top cell. But when it is textured, you will see that perovskite materials cannot form on the texture surface very efficiently. That's why I will mention it when it comes, that they make the surface flat and then they continue to fabricate the solar cell on a flat surface. But texturing help for the mechanical stack, or if the above top layer filters. And if you have 4-terminal, if you have 2-terminal mechanical, it is advantages. And with this structure, for example, with the 2-terminal device, we had 14.6. If we use silicon heterojunction as the bottom cell, which is high efficient, and the 4-terminal, we could achieve 21.4% efficient. This is the earlier tandem studies. Again, we continue with the earlier studies. One of the first studies of tandem solar cells is here at 2015, and that time they used spectrum splitting. As I said, as I showed the device structures, the splitting can be done, but it is not feasible, I guess. What they did is they split the spectrum at 550 to the perovskite and crystalline silicon heterojunction bottom cells separately, and they could reach twice of 28%. And again, earlier tandem studies, this is the example for 4-terminal studies. They used similar mesoscopic top cell and silicon heterojunction bottom cell, like we did. And in this case, they used molybdenum oxide as the recombination junction. Even if it is stuck together, you need a conductive layer for the recombination, right? That's why they use molybdenum oxide here and ITO on here with the silver grids. And this is 4-terminal. That means they have the efficiency separately and they add it together. But with filtering, they had, again, 13.4 efficient solar cells. And this is the example for earlier tandem studies. Again, 2-terminal example for monolithic tandem structure. It is one of the, I guess, one of the first studies at 2015 as the monolithic structure. You see that they fabricate the perovskite solar cell just stuck on the silicon solar cell. That's why you see it as a standalone solar cell. In this case, the recombination junction is a heavily doped N+ layer, which makes the barrier and connects make the tunneling. And This layer here acts like a recombination junction and make two-terminal monolithic tandem configuration with the efficiency of 13.7. One of the monolithic devices in tandem solar cells. If we come more recently, you will see that almost the cell is similar with the crystalline silicon heterojunction solar cell because of the high efficiency mainly. You can see different recombination junction trials like nickel oxide topped with PTA double layer maybe. And here are the views of the SEM images, and you can reach with this monolithic, again, these are monolithic two-terminal device with the efficiency of more than 90%. And these graphs you will see in others too. These graphs shows the capability of the absorbance of perovskite and silicon parts that you can see how much current you can have from each device. Okay, so here's an example again with the silicon heterojunction bottom device. They make the surface flat and they introduce recombination junction with the ITO again and building perovskite solar cell on it. You can see in some structures like magnesium fluoride front surface or lithium fluoride. This is usually act as like anti-reflection coating, the same phenomena as I explained before. And here are the EQE, quantum efficiency graph, and again, the front perovskite top cell and the rear side of the bottom cell. This is the certified efficiency of 29%. They reached 29, more than 29, but certified efficiency is around 28% efficiency, which is also a recent study. But of course, it doesn't have to be silicon all the time. The bottom cell can be changed. You can. There are a lot of research with other structures, other cell types. For example, in this one, CZTS selenide band gap, and the perovskite, transparent perovskite is 1.68, 65 here, electron volts band gap. Again, you see that this is the standalone CZTS selenide solar cell with the high current, but the limiting current here is this is transparent perovskite, you see, and the tandem device is limited in this current, but you can add the voltage because it's seriously connected, and you can have efficiencies like 17.6 in this device. The others are like, this is an example of all perovskite tandem solar cells. In this kind of solar cells, you have bottom cell perovskite and top cell, again, perovskite. So because, as I said, it is tunable, you can tune the band gap. You can use low band gap perovskite material for the lower cell and high band gap perovskite material for the top cell. And here, the recombination junction is, again, very thin layer, thin gold layer with the tin oxide. Layer is the recombination junction here. Here is a SEM image of it, and the efficiency of 24.1 is achieved. And you can see the drivers of efficiencies and GSC, FF, other parameters of the solar cell. Again, as I said, the bottom and top cell can be changed. This is other example to use CIGS solar cell in case of as a substitution to the silicon solar cell. It has band gap of 1.1, and the perovskite top cell is around 1.68. So it's a good tandem, monolithic. These are all monolithic tandem solar cells. Recently, you can see a lot of researches on monolithic tandem solar cells. This is with the efficiency of 24.2, and they provide the IV here. This is the certified IV by Cell Lab Fraunhofer ISC in Germany. So what is next? What kind of research is going on next is, one example is here, as the triple junction solar cells with the bottom silicon heterojunction bottom cell, middle cell as with the perovskite, and the top cell with the perovskite. You can have 3 different solar cell in the same standalone 2 terminal, but it has still lower efficiencies. Actually, theoretically, they have very high potential, but still around 20% efficiencies they provide. So now I will cover, in coming slides, I will be covering the current situation of the photovoltaic technologies in the market. What kind of technologies we use in the market, and what is the forecast? What is the possibility that we use them? First thing, we know that the crystalline silicon photovoltaics dominate the market with the 98% of the market. So this is the data for 2024, are crystalline silicon solar cells. It is well-established, well-known technology, state-of-art, reproducibility is very high. That's why have very good advantages. And that's the thing, actually. We try to use silicon in tandem cells because silicon have the theoretical limit with single junction, and it reached the limit around 30% efficiency. And to exceed this kind of efficiency, we need tandem-like structures. And because we know the crystalline silicon manufacturing very well, and lines are established everywhere, that's why we try to use these for cost efficiency. We try to use this technology and build on it. So this graph shows the different wafer material types. We see that P-type crystalline silicon materials and N-type crystalline materials on the market, but mostly N-type wafers are used for the high efficiency. And by the 2035, we will see that the share of P-type will be very low. If we check on the different cell technologies, we can see that the dominant technology in the market now is PERC and TOPCon's technology. And in the world, this is the average of world, I guess. And this is the data of 2024 with some other technologies have some part, but mostly PERC and TOPCon solar cells. And it seems that PERC solar cell market share of PERC solar cell will be diminished in 10 years maybe, and the TOPCon and others type of solar cells will come through. And here are the share of crystalline silicon-based tandem solar cells expected to take place from 2029. Of course, these are the forecasts. And the bifacial silicon solar cells, the monofacial silicon solar cells share is like this. Mostly bifacial solar cells are used, and monofacial solar cells still be there, but the most dominancy will be the monofacial, the bifacial solar cells because of the high efficiency maybe, and with the well-known technology again. And if you look at the efficiencies, these are the average stabilized efficiency values for silicon solar cells in mass production, that the PERC values is expected to be stabilized around 24%. And here, the crystalline silicon tandem solar cells, it is still on research. That's why it is expected to rise and reach around 32% efficiency, and this is higher than the single junction limit. That's why in some part of the technology, this kind of tandem solar cells will be in the market, but it is just a matter of time, I guess. So among the tandem solar cells, what kind of structures can be in the market is here. It is expected that from 2007 we can see some tandem solar cells in the market, mostly N-type silicon bottom cell with the perovskite top cell, and maybe some perovskite tandem cells may take some share. But for the forecast by 2035, we see that the crystalline silicon with the perovskite tandem is more expectable to have the share. Okay, I will summarize the talk here. It was a little fast, but I will summarize the talk with this slide, that the renewable energy is essential for a sustainable and low carbon future, and solar photovoltaic technologies are the fastest growing renewable technology and will have more share in the market. Silicon-based solar sets still dominates the market, and as I said, we don't want to give this technology up because everything is there, established, everything is well established. That's why we try to use them as a tandem part. And advanced solar cell designs like PERC, TOPCon, and tandem solar cells continue to improve, and the integration of the innovative materials and architectures, different designs will shape the coming generation of solar cell technologies. Okay, this was my presentation today. Thank you for listening and coming to presentation. If you have questions, I can answer.
Thank you, Professor Abdullah Üzüm, for your valuable presentation. Yeah, some of material I myself just know about the advance of the solar cell technology. Yeah, and before going to the question and answer session, I would like to introduce myself first. I'm Rahmi Andarini. I'm from Engineering Physics Department, Universitas Multimedia Nusantara. And there is also Pak Agi Maliki. He's also a lecturer from Engineering Physics Department. And I also have some students here from Engineering Physics Department. Now they are in the second and third years, and they are taking a lecture on energy and environment, and also energy conversion. So for the next session is question and answer session. I would like to offer to Mr. Agi Maliki to be the moderator of this session. Thank you, Professor Abdullah Üzüm.
Thank you very
Please,
much.
Pak
Thank
Agi.
you.
Okay, thank you, Miss Rahmi. Okay, any question from students, especially physics engineering students? Maybe any questions about the presentation? It's really good presentation. It's very detailed and give us insight about new technology in solar photovoltaic panel. So, any question? Maybe? Okay. Let's start from me, Mr. Rahmi. I give push. Yeah, I give push. Okay, Mr. Abdullah, thank you for your interesting presentation. I am Agi Maliki. This semester I am teach renewable energy class. Yeah, so this is very valuable knowledge for me and for my class. So I have several questions. The first is from your perspective, how soon could perovskite-based or tandem PV technologies be integrated into global solar market, especially in developing country?
Uh,
Thank you.
yeah, yeah. I can say like this, that you can hear me, right?
Yes.
Okay. Uh, that's my opinion. With some, I can say like this. As I said, crystalline silicon solar cell technology is well established, and we know everything. The reproducibility is very, very well. But for perovskite solar cells and even tandems, we don't have that kind of state of art yet. If you check, you will have in every paper you have different materials, different mixtures, etc. And even the technologies are even not complex. The production is very sensitive. That's why it is still difficult to make it reproducible. That's the main challenge for the market, I guess, for perovskite. It is same for the tandem solar cells because it is very highly uh, expectable to use perovskite on the tandem structures, but the same thing goes for the tandem. Recombination junctions are still the problem. The toxicity of the perovskite because of lead is still kind of problem. And the stability, other problem, because it is going well now with the stability, but these are still some challenges because for the market, we need these kind of measures well established. And I believe that by time, it will take some more time, but it will start with the advanced economies, with the countries with advanced economies. That's why after that, maybe the growing economy, growing countries will come after that. But I guess we still have some time.
Okay. Thank you for the insight.
Thank you.
Okay. Any question from my student? Maybe. This is
Uh,
really, really good
Lecture.
lecture. Yeah. This is very
I don't know.
detailed.
I don't know. Maybe I tried to cover the key points for each
Yes.
part. That's why I didn't want to go a lot detailed. But of course, if you have questions, students just ask. We can discuss, and
Yeah.
let's see.
May I ask a question,
Sure. Sure.
Professor Abdullah? Yeah, regarding your research, that we know that that's for me it quite very advanced compared to what we are doing now in our university. Yeah, my question is that how to convince to the market that this is now still in the research stage, and according to your experience in Turkey, for example, is that what is this kind of research? Because so far I know that you made it your research in Japan, if I'm not mistaken. Yeah, when you bring your result of your research to Turkey, uh, how how was the government support this research and implemented it into the market, or implementation in what is not only in the research stage?
Yeah. It was like this actually. The data I showed uh, about perovskite part, the its crystalline silicon part was general. I mean, it's a general part, but in perovskite part, mostly from my postdoc years,
Mm.
I wanted to show at that time that what kind of these were the first researches, especially on tandem side. That's why I wanted to show how it began. And when I came back to Turkey, it was very new technology here. And still, I don't know about Indonesia, but for example, in the market, we have TOPCon recently. Recently, TOPCon solar cells we have in the market now. It was mostly PERC solar cells. And now, after I came back, I actually, with the projects, because it is new technology, tandems have a good future, I guess. That's why for the research side, it was more easier to convince to make some research on it. But the problem is if the toxicity of that is, I guess, the most important thing for the research side to take care, because it can be really toxic even in the research side, a lot of chemicals. And for the market, it is still have time. For us, we have a lot of time. But now in Turkey, in Turkey, we have a lot of some other groups working on perovskite. But recently, I don't work on perovskite actually, mostly about some semiconductors and crystalline silicon. But for the research side, it is still new technology, very promising technology. You can start to work on it, but when we start to work on this kind of technologies, it is important to start after one step. I mean, you need to grow fast and to reach the tandem, and it will make more knowledge. But for the market, to convince the market, it is not easy. It is not easy, especially for developing countries like Turkey. I mean, it will have some time for us, I guess.
Thank you. So I over to Pak Agi again.
Okay, any question? What? There's no question. Okay, I might ask again, Mr.
Okay.
Abdullah, because
Yeah.
I wanna know about implementation about solar energy in your country, Turkish. There's any policy or incentive from the government to Turkish people if they wanna change to renewable energy, especially the solar energy? What kind of strategy Turkish government make to make people wanna switch to solar energy? Thank you.
Yeah, these kind of strategies and policies actually changes very fast, not only for Turkey, for other countries too, I guess, with the feed-in tariffs. But in Turkey also, they encourage people to install even rooftops and governmental sponsorships for the part of the large applications, utilities. And for example, recently, now you can make the rooftop panels, for example, for you, even if it's excessive energy, you can sell it to the government. And you use for example, let's say you have a 6 kilowatt power system, photovoltaic system, but you use only 4 kilowatts, and the excessive can be sold to the grid directly. And at the end of the month, you have the bill for your consumption and for your how much you consumed, how much you sell, and which side will give money to other side. If when it is grid connected, it is if you excessive more than you have the energy, then you need to give some bill. But if it is vice versa, then the government will give you back the money for the power you sell to the grid. But even these kind of strategies still changes. They try to encourage it. For example, now you can make without license up to some kilowatt systems for yourself. But of course, there are also some capacities established for the different regions. And these are changes very fast. And recently, in general, it is growing very fast in Turkey, I guess I can say, because recently both government have a lot of encouragement for the tariffs, and they established new large systems, and now the people in Turkey know photovoltaics better because they started to see outside very well, and with the small applications too. That's why in general it is going fast, and the encouragement is changes by time, but it is still there. And what about the Indonesia? I mean, how is it there?
Almost 5 o'clock in the evening. Yeah, 5 o'clock.
Okay. So other thing, I meant the station of photovoltaics in Indonesia, not the time. But anyway, other thing is now Turkey has the share of 11 around 11 to 14% of share of the energy usage in Turkey from renewables, photovoltaics only. That's why the share is great. I mean, it is, and we have the balance. Balance is important, I guess. We have the balance of hydro, photovoltaics, wind, and fossil fuels. There is a good balance now, but I hope renewable energy will go upwards. And how is the station of renewable energy in Indonesia? Is it growing or?
It's kind of funny because some years ago, I remember if people in Indonesia installing a solar panel producing energy, and then the energy is excess, then the government will give a penalty to them.
Really?
So
Okay.
really, it's kind of funny policy.
Interesting.
I don't understand
Okay.
how like that. So in Indonesia, the renewable energy in general still growing, but in slow pace because Indonesia is one of coal producer, coal,
Yeah.
and we still use them. And the government seems like not really want to change the coal because the coal is cheap. Electricity from the coal is really cheap.
Yeah.
So yes, the renewable energy is there. We have geothermal, we have solar energy because we in equator, but yeah, just like that, not really at
Yeah,
good
it's
pace.
developing. It's similar. I mean, in developing countries, I guess it is not. There's no big differences. Yeah.
Yes. Okay.
Agi,
Any?
I think there is student raise hand.
Okay.
Please.
Please.
Hello, sir. and Miss.
Hello?
Yes.
Uh,
Uh,
is my
please
voice.
mention your name and where are you from?
I am Trudy from Sir Agi and Miss Rami student. Professor Abdullah, I want to ask a question. Is there any major difference between installing solar panel in Turkey and Indonesia in your perspective? Perhaps the landscape or some requirements that need to be fulfilled.
I couldn't hear very well. Can you repeat the question? Between Indonesia and Turkey?
Okay. Is there any major differences between installing solar panel in Turkey and Indonesia in your perspective? Perhaps the landscape or some requirements that need to be fulfilled.
Okay. So
Thank you.
the installments, I am not sure about the Indonesia, but it is difficult to guess because the installments of the solar PV systems is both economical and the feasibility. Feasibility is, I mean, where you install the larger systems and how you install it. I guess we have landscapes that you can make solar farms, but if you look at the radiation data, I guess Indonesia is more favorable to because near the equator, it's more favorable to use. We have less sunny days, sunny hours, I guess. That's why if I compare both, I guess you are more favorable there. But about the if there's a major difference or not about the installments, I don't know the installments very well in Indonesia, but in Turkey it is growing, as I said. But what I guess is similar is the growth of the renewable energy, especially PV, solar PV. I guess will be similar with the trend in case of the installments. But it is about the economy, it is about the perspective, if you want to install or not. It is about the decision of the governments, what kind of scenarios they have. It differs very much. That's why it is very difficult to say an exact thing.
Okay, Trudy.
Okay, sir. Thank you.
Okay,
Thank you
this
very
is
much.
a question from Bertrand. Okay, Bertrand. Halo,
Veteran sini aja. Veteran disuruh.
Bertrand.
Veteran disuruh.
Any question, Bertrand and Alvin? Alvin. Alvin, can you hear me?
Hello, can you hear me?
Okay.
Okay, greetings, Mr. Abdullah. My name is Bertrand Emmanuel from Engineering Physics 24.
Bertrand.
Yeah, I would like to ask a question regarding the environmental impact of creating the solar panel, because solar panels are often called clean energy, right? Clean energy sources, but obviously the creation would still create some impact, especially on the environment. How serious is that? I mean, how serious is the effect on the environment? That is my question. Thank you.
Okay, a good question, because there are a lot of discussions on this side going on that, okay, we say that solar PV is clean, but if you look at the process, we have a lot of chemicals, dangerous gases, etc. So the manufacturing side is not that much clean, maybe, but we think that we recycle them. I mean, But regarding to your question, after manufacturing, now we have solar panels with a lifetime of around 20 years, 25 years recently. But if you look at the advanced economies, advanced countries like Germany, for example, I always give this example that they started to install PV solar panels earlier than us, a lot earlier. And now these kind of countries, and now us, after 20 years, it will be us that have a lot of panel garbages. So that's why there is another research site for recycling research. There are some researchers, the research groups all over the world. They try to recycle the silver from the used panels, for example. They try to recycle aluminum. They try to recycle the metals, materials from the solar cells that are already done, that you cannot use. That's why, okay, it is clean, but as you said, we need to make this recycling more effective before the manufacturing and after the lifetime of the solar panels. And if the manufacturing of these kind of technologies and after the lifetime of these kind of technologies, if we recycle them 100%, then it will be totally clean, I guess. Thank you
Thank
for
you.
your question.
Okay, nice question, Bertrand. Okay, next, Alvin. Alvin, you have a question? Can you hear me, Alvin? Okay, Alvin. Okay, next this is a question from Sarah, Prof. Okay, Prof. Abdullah, do you think that can we solve the market problems more quickly and implement a plan to convince renewable energy institution in Europe to support us financially in Turkey or any country with advanced solar energy project, for example, like Indonesia? How many years could this take? Is it dependent on researcher the most to find solution?
I guess for the convincing the renewable energy support institutions in Europe, it's not necessary because everybody, for especially Europe, they want to use renewable energy and they have very well supports projects, international projects, etc. It is there. I mean, they try to support in general, but recently all over the world, you know that economical life and spendings are not so well. So every country now try to cut the finance from some points. So that is hard to say that which country cut the finance from which kind of projects, etc. It can be different in Europe, it can be different in USA, in Indonesia, or in Turkey. That's why it is hard, but making projects will be possible. It can be possible, but and still renewable energy is, as I said, going on technology with very promising topics. That's why it is the important thing is when you submit a project or when you think about the solution, you need to think you need to think the feasibility of it. I mean, that's the most important. That's what they want to hear. I mean,
Yes.
if they want to support it from the government, you would say that, okay, I
Feasible.
make this solar cell, inshallah,
Feasible.
but it will be lead-free and there are lead-free projects, for example, for perovskite, there is no environmental effect, there is no, it is not dangerous, etc. And for example, now the stability is the big problem, and the integration of the perovskite to the module side as a module is another challenge. So these are the new challenges. That's why I advise to think about these kind of challenges to make it easier to convince. But hard to say a specific thing now. I guess there is another question in the.
Okay, that's a question from Sarah. There is another question, Mr. This time from Lea Devosadewo from Telkom University. The question is, does the Turkish government support the renewable energy? And what percentage of renewable energy has been installed in Turkey? And what power plants are currently in Turkey? Maybe his mean power plant of solar energy, maybe.
Yeah. In Turkey, as I said, the government supports the renewable energy, and they announced the policies changes very fast, but in general they support. And now in total, all over totally, we have 120,000 megawatts of installation. That's the all energy we have. I mean, all total power from including fossil fuels, etc., everything. And last year, the share of renewable energy, the share of solar plus wind energy was around 30%, and 19%, I guess, I need to check, but around 19% was from solar PV. Actually, that's why it's a good share, I guess. So in total, renewable energy case, including wind, solar PV, hydropower, thermal power, etc., hydropower, big and small hydropowers, these renewable energy goes more than 50% share in Turkey now.
Okay, thank you for the answer, Mr. That's a question from Leah. Okay, one last question, maybe. There's any question? One last time. Any question? Okay, seems not not question. I give to Mr. Rahmi, Miss Rahmi again, because there's no question.
Okay, thank you, Pak Agi, for guiding us during question and answer session. Yeah. Again, thank you, Professor Abdullah Üzüm, for
Thank you very
your
much.
interesting presentation. Yeah, I have some notes from this from today sharing knowledge. Yeah, you already sharing knowledge regarding the renewable energy, which is it is known as the alternative energy to be more clean earth and less or zero emission as well, and also about the advance of the technology of solar PV. And there is also notes from the question and answer regarding the opportunity for research, because there are still more research to do, and also the research regarding the waste of the solar PV, for example, the chemical, and also there is still opportunity on how to be more clean in order to manage the waste of solar PV. And also before I close, if there is some student or lecturer interested in like visiting your laboratory, or if there is opportunity for cooperation, will you be welcome to
sure.
to this initiative?
Yeah, sure. As I said, we are open any kind of collaborations, exchanges. Our students can come there with project or something. Your students can come here. We are very welcome for you, the professors. Just anytime we need to get in contact, and we can see what we can do, what we have, what kind of collaboration we have, what you and us in this side too. Why not? It's research, so it's we are always open this kind of collaborations.
Okay. Thank you, Professor Abdullah. Okay, last but not least, would you mind to give us the like closing statement before I close this sharing session?
Yeah, just few words maybe. At first, I want to thank for the students in class and to online participants to for them to listen my presentation, and it was very nice to meeting you and students even online. I don't like online lectures, but I prefer face-to-face. But it is still nice to meet you with class, with students. Thank you very much for the questions, nice questions. If you have any, you can still ask. And I hope we can continue the collaboration. We can see what we can do, and we are always open. And thank you very much for inviting. That's the first, and we hope this kind of collaborations can go on. And yeah, thank you very much for today. That's all I can say.
Okay, thank you very much, Professor Abdullah. Again, we want to have a together picture, even though we are now not in the
should I?
face and face mode. Maybe Pak Agi, or who can help us? Please open your cam, the participant, so we can
screenshot.
Yes,
Miss Rahmi, I cannot tell. Okay, how to make this?
Rafa, you there? Sarah, Bapak Yadi, Mas Yadi. Oke.
Bu Rahmi saja Bu yang ini.
Oke. Vanessa, where are you? Okay, you are in the class. Okay, together. Arif, Aditya, Jessica, Fauzan. Okay. Please open cam. So.
Oh, there is another class. Okay.
Yes. Okay, so I will start to count. Please smile. Give your best smile. 1, 2, 3. Okay, I'll go to next page. Please. Still okay. Wait. I will go to the next page because there are more participants. Please open your cam. Novella, Lucia Trudy, Muhammad Iksan, Azhar, Fauzan. Okay. I will start to count. 1, 2, 3. Okay. Thank you very much. And again, I appreciate for your attending this sharing session. And again, Professor Abdullah Üzüm, maybe this is not the first and not the last for you to share your knowledge to us. Hopefully there will be another collaboration and opportunity for us to have your lecture. Thank you
Why not?
very much.
My pleasure.
And
My pleasure.
thank you very much and have a nice afternoon.
Thank you, Mr. Thank you, Mr.
Good
Abdullah.
evening. Thank you very much. Thank you
Assalamualaikum.
very much. Alaikum salam.
Hello.
Oh,